Thank you, Captain.
You need an extra camera so you can film whatever you're going to be doing with the camera.
Oh, no. All right, guys, let's look at household circuits. Everybody has smartphones, except for me. Give me just a second. Right.
Yeah.
We had to pull out our cell phones. Yeah, I'm glad that I used you. All right, guys. So we're going to look at household circuits. Hopefully, we'll wrap up this chapter today. If not, we'll wrap it up on Friday. In your house, you have we're looking at a number of different safety features, and then also just sort of how your house is laid out. First of all, you have 3 wires that come into your house. So if you look at your house, you have this thing that comes up on the side of your house. It sort of looks, I don't know, it's called a service head. And you have 3 wires that go into this. You have 1, 2, 3 wires. If you look at this, you can see them sort of coiled together. And these all come off of a transformer outside of your house. So you have your utility pole, and then there's a big can, and then there are 3 wires that come off of this, and these 3 wires go directly into your house. Is this we talked about transformers. Do y'all remember if this is a step up or a step down transformer? It's a step down transformer, and what that means is that it takes high voltage electricity and makes it low voltage electricity. We'll watch a video in a few minutes about this, how these transformers are made and what they do. They operate by an idea called induction, which we'll study next semester. Basically, whenever you have an alternating magnetic field, a magnetic field that is changing, that magnetic field can generate a current within a conductor. And so we'll talk about that next semester, and also why we use AC, which is alternating current, versus DC, which is direct current. Alternating current just means the current changes, it oscillates by plus or minus every so often by a certain frequency. And we've been talking about direct current, meaning that the current is just constant all the time. But in our homes, we use alternating current. Now, a lot of our circuits, they can be dealt with the same way that we've been doing, whether you have alternating or direct current. Next chapter, I'm sorry. Yeah, there's a 3rd semester now. Actually, if you're pre-engineering and you're going to LSU, they now require 3 semesters in the whole state of Louisiana.
What's the 3rd semester?
Huh?
What's the 3rd semester?
Well, typically they split up the topics. So they
Intro, right?
Huh?
Intro to physics for this one.
No, you do kinematics, basically, class. Then you have heat, sound, and light. That's the 2nd semester, and electricity and magnetism. That's the 3rd semester, or something like that. I think heat, sound, and light is actually the 3rd semester.
So which one are we just using?
We typically don't do sound.
We don't do sound.
Yeah. And then it's sort of more compressed, so they'll go into greater detail. But we decided that a couple of years ago. I think it'll be good. All right. So,
Am I good for you now?
huh?
Am I good for you?
I think so. Yeah, this was just a recent change at LSU, but LSU generally drives the whole state. So you'll be good. You might have to take a 3rd semester when you get there, if you go to UNM.
That's fine. I'm just making sure that my transition,
Yeah, shouldn't be a problem. The whole point is in the state is that they want credits to be able to transfer more easily, and so we all got together a couple of years ago and decided these are the topics that we're going to cover in these classes, and that way they'll transfer more easily from one university to another. All right. So anyway, 3 wires come into your house off of a transformer. This is a step-down transformer. It means it takes high voltage electricity and makes it lower voltage. These wires that come off the transformer, they include 2 hot wires. That's a plus 120 volt wire and a minus 120 volt wire. These collectively are called the hot wires, meaning they have electricity coming through them, and a neutral wire. It's like a ground wire. So it doesn't have electricity unless you're actually operating the circuit. And so the plus 120, for example, would feed into that neutral wire. We'll talk about that in a second. I have a little video. This just it's a few minutes, and it's from the Discovery Channel, I think. And they talk about how transformers are made and how they operate. Now, again, they're talking about induction here, and we'll get into that next chapter. So let's watch it. It's sort of just for your own interest.
New video.
Yeah, it's not really.
I'll stop it.
That guy really wants to talk.
I like that guy. All right. So here's a little schematic of what happens when this comes into your house. These are your two hot wires. Remember, this is plus 120 and minus 120. They come in. And then you also have that neutral wire. These both go, or all three of these come off of that transformer, like we saw. These all three go into your meter, and then they go through a circuit breaker. And then your circuit breaker, this would just show one circuit, for example, in your house. And you might have anywhere from 10 to 30 different circuits, depending on how big your house is. On this circuit breaker, you might have different things. So, for example, you might have a lamp, radio, or whatever, microwave. So each of these would represent something different. And then in your house, you would have multiple circuit breakers, right? As I said, 10 to 20, 30 or so. Now, this household circuit is laid out in parallel for a couple of reasons. We've talked about this a bit. The first reason is so that everything operates at the same voltage. Every device operates at 120 volts. Whereas if things were in series, that wouldn't be the case. Some things would operate at one voltage and other things would operate at another voltage, depending upon what was on at the time. So like if you turned your toaster on, that would change the voltage for everything else in that circuit. The other reason is so that if you turn one device off, everything else doesn't go off. So if you turn one device off, the others remain on. If you recall with the old Christmas lights, where if you took one light out, they all went out, that was because they were all in series. And so, but if you have things in parallel, you don't get that problem. We're going to talk about several safety features in a household circuit. The circuit breaker, the grounding of your home, and the GFI, or the GFCI. Circuit breaker, grounding, and the GFI or GFCI. You can call it either, they're the same. All right. I'll tell you in just a bit. The GFI, it means ground fault interrupt or ground fault circuit interrupt, but we'll get to that in just a bit. Yeah, we'll get to it. Okay, so circuit breaker. Most of you will have circuit breakers in your home. You'll have a box that looks like this, sort of. Some of you, if you have older homes, might have fuse boxes. We have fuses in our house. Our house is built for 50s. So actually, we have fuses and a circuit breaker because the circuit breaker's been added since. A fuse looks something like this. It sort of looks like a light bulb without the bulb part, and it just sort of has like a metal or a glass top. If you look on the top of the fuse, it has a little window, and then there's a little metal tab inside of the window. And if the fuse ever blows, well, the circuit breaker and the fuse are there to limit the amount of current. And so if the current exceeds a certain amount, then the circuit breaker will turn off. If the current exceeds a certain amount on a fuse, what happens? It burns up that little metal tab. And so if you have a fuse that's spent, that's blown, you'll see this is all black, and there'll be soot like in that window. Or you'll just see the metal tab is broken. Was that?
In other words, you got like double protection kind of thing? So you have both things?
In my home?
Yeah.
No, our fuses operate for some of the high voltage devices.
Oh, so not for the whole house?
No, right. On your circuit breaker, you also have a main breaker handle on a lot of the newer houses. That means you can turn off electricity to your whole home, right? Just turn everything off all at once, and that disconnects you completely from the street side service. So if y'all are in hurricanes, right, and y'all know how to, I'm not going to tell you how to energize your whole house. Have y'all done this before? You're not supposed to do this.
You plug it into a high voltage, and you're supposed to turn off a lot of people do it, but you're supposed to turn off your main circuits because it'll feed back into the line.
Right.
And any of the energy people who are working on the lines may not know because they're assuming, hey, everything for miles is off.
Right. So if you have a generator, you can take it and you can rig up an extension cord. So you're not supposed to do this, and it could be dangerous. But you can take an extension cord and put 2 male outlets, like 2 plugs, 2 male plugs like this. So have one on each end, and you plug one into your generator, and then you plug the other into an outlet. And whatever other outlets are on that circuit, the generator will charge. Right? Or like ceiling fans or whatever, it happens to be on that circuit. But the problem is, as Scott said, is that if you do that and you don't turn the main breaker handle off, then that means electricity will go out of your home and into the lines, and it could hurt somebody if they're working on the lines and don't know that there's actually electricity.
So you need to know what you do before you do it.
Yeah, it's probably not a good idea. Just run your box fans off the generator. All right. So a circuit breaker or a fuse turns off a circuit if the current exceeds the safe capacity of the circuit. And most household circuit breakers turn off if the current is bigger than 15 or 20 amps. So sometimes you'll have, or often you'll have additional circuits in your house. You might have 2 switches that are right next to one another that are connected, and those will be 30 or 40 amp circuits. Those are for like what, for example? Bigger things, yeah, bigger appliances, dryers, stuff like that. So your typical circuit's 15 or 20 amps, and sometimes you'll see it'll be written on the switch. Right? So that's our circuit breaker. It just turns off if our current exceeds a certain amount. So Lauren, for example, if you had a big surge that came in from the street, your circuit breaker would be your first home defense. Though the power company, they also have circuit breaker-like things on the power lines, things that will turn off electricity to a section if there's a surge of current through the lines. That's why what? Yeah, I don't know how they work. I think they're just like circuit breakers, but they have these long cylinders. They're like big switches, and they turn off like if a bird lands on the line and shorts it or whatever.
It's a big bird.
No, whatever, yeah.
But it's a touch too, the ground line and the thing line.
All right, the circuit breaker works like this. There are a couple different types. This is the first type. I don't think they use this type anymore, but they use a bimetallic strip. You remember the bimetallic strip, the used part that we talked about last semester? Oh, we didn't do thermal last year. You'll have a thermostat in your home. Some of you might have the really old thermostats. They're like a rotary dial-like thing. You pull them off. What do you see inside of them? You ever done this? No. But if you pull those off, if you have those rotary dial type, the really old thermostats, you'll see a coil of metal inside. That's a bimetallic strip. And a bimetallic strip will coil up or coil back if it's heated or cooled, because the different metals expand at different rates. And so this uses a similar thing. I have a bimetallic strip right here, and the current goes through that bimetallic strip. If the current exceeds a certain amount, it heats up that bimetallic strip and will cause it to bend one direction or the other, and it'll turn off the switch. Most circuit breakers actually have an electromagnetic switch, and we'll talk about this next chapter. This is called a solenoid switch. Jose?
So when temperature goes back to normal, or do we just go back to the same place? And
No, when you're...
stay bended to whatever?
Yeah, let's see. The switch would turn off, and then you'd have to come back and turn it back on. So if this metal bends, how does that work here? If the metal bends back this way, if the current is too big, it's going to disengage the strip bar.
Okay.
Is that right? I think that's right.
It's expensive.
No. If it goes this way, it pushes it over here, and it turns off the whole circuit. Right? And then you have to come back and flip it back to where it goes. The on position.
Okay.
All right?
I know.
This stuff, don't worry about the bimetallic strip and all that. I think it's kind of interesting, so
Okay.
now
What's the pure supply?
Here, most of them use an electromagnetic switch, and we'll talk about this next chapter. When we talk about solenoid switches use a permanent magnet and an electromagnet, and through the interaction of those, they can cause a mechanical movement. They're kind of cool. You use these in your car and the starter. That's called delay. The solenoid part of your starter, and you use them for a variety of purposes. So basically, you have an electromagnet. And when you run a current through it, it generates a magnetic field, and it causes it to move if you run too much current through it. Let me show you another picture. This is a picture. Let me show you a diagram. So our current comes in here through this wire. It goes around this permanent magnet, and then it goes through these contacts. However, if I get too much current through here, it causes this permanent magnet to come out, to move, and it opens up that switch. You don't really need to know how the circuit breakers work, but just that they turn off when the current exceeds a particular amount. Let's try this quick test. This is a little calculation. So here, on a 120 volt circuit, I have these three devices that are operating, and I add a fourth device, this 480 watt television, and the circuit breaker turns off. So I want to know, what is the maximum allowed current for this particular breaker? Now, remind you, the power is equal to the voltage times the current here. And so you need to figure out the current for each device, and then figure out what is the maximum current on that breaker. About 15 more seconds. Or we'll go to 2:36. 10 seconds. Just a few seconds. All right, very good. C is the right answer. Let me show you. We first want to figure out how much current is on the circuit as it's operating. So I find out the current for each. That's going to be P over V. So here I have P is 1200. That over 120 is going to be 10 amps. This is going to be 1 amp, and this is going to be 1 amp. So initially I have 12 amps that's operating. And then I add this, which is 480 watts, or 4 amps. So 12 plus 4 is 16. It was operating fine at 12 amps, but then the circuit breaker turned off at 16 amps. So somewhere between 12 and 16, it turns off. And so the only number between 12 and 16 is 15 amps. All right. Let's look at grounding. This was added to houses around in the 1960s or so, and you can retrofit a house to have your outlets all grounded, but the way to do it now is to take a grounding rod. It's a copper rod. It can be pretty long. I think it's supposed to be like 6, 7, 8 feet long. And they drive it deep into the ground. If you go outside your house and look where the wires from the transformer come into your house at the service head, if you look down at the ground, you'll find this grounding rod. It'll look a lot like this. Be really close to your house. And then there will be a wire attached to it, and it'll go up into your house. Now, when we have grounding of our outlets, here, it's like these, this third prong on your outlet, the sort of oval-looking thing. It connects that prong directly to this grounding rod. So you have a direct path to the ground. It serves two purposes. The first is to protect you from faulty devices. I'll show you how that works in just a second. All right, and then the second, and I think this is a lesser purpose, but I understand that it's still a purpose, is to protect you from lightning strikes. So if you have your home and you have these wires that come into your house, if lightning strikes, oh, y'all get the idea, right? Yeah, if lightning, that's a pretty good lightning bolt actually. If lightning strikes your house, you get this surge of electricity that will come into your house. And, you know, my grandmother used to tell this story. My grandmother is sort of known to tell stories in sort of hyperbolic way. But she said that one time lightning struck her house, and it was before grounding, that we had this grounding of our homes. And the electricity came in, and of course it fried everything in the house. But she said that the television started dancing around and sparking and stuff. I'm not sure that that's true. But you know, obviously lightning in your house can be a problem with that great surge of electricity. But what this does is instead of allowing it to come into your house, because really electricity just wants to get to the earth, basically. The earth is like this great big sink, and all the charges can just go right into that sink. So really, it just wants to find the easiest path to ground, and what that does is it just provides a direct path to go down into the earth. Right? Instead of going into your house, it goes into that grounding rod.
Quick question.
Yeah.
We have offshore. We have to put all of our equipment, even stuff that doesn't generate electricity. We have to ground it with plastic. Because I mean, we'll have like compressors, things like that that don't even. They made us this year start attaching ground wires and attaching it to the platform, even though it's a metal connection. You know, because the metal frames will be touching the metal platform. We still have the ground.
I'm not sure, Rob. Maybe it's some atmospheric thing that you can get a lot of charges built up on any device.
These things aren't even producing electricity.
Yeah.
I understand if it's producing electricity or something to ground it, but
I don't know, but I know that like in firefighting, that I think this is true, that if you're using one of these like a big fire extinguisher, you're supposed to leave it on the ground. Am I correct in that? I think that's a similar thing to keep it grounded.
Not really. If you're using it, it'll build up charge, but you're wearing full gear, and the second you put it down, the gear is a little bit electrical resistant. It's just a lot of thick gear.
All right. They taught us this in the Navy, so maybe it's a similar thing as what you said, because you're on a metal ship.
You were in the Navy?
Yeah. Just for a couple of years. But anyway, so.
I could get on the boat.
And I don't have a cell phone. And I used to be in a heavy metal band.
I could get on the boat if you're using the thing, since it's not really grounding. And
Okay. Anyway, so this is our outlet. All right. This goes directly to that third prong outside, or directly to the grounding rod outside your house. But in older homes, you don't have that. By the way, you know, on your outlets, typically, you notice how one of these is bigger than the other? Typically, this is the hot wire, and this is the neutral wire. So if you really want to impress your friends and make them think that you know something that they don't know, you can take a paper clip And you can stick it in any one of those except for the hot wire. Like you don't want to stick it in this one because that would be very bad. You can take a paper clip, you can put it here. I mean, I would be comfortable putting it there because this just goes to the ground outside. This has no electricity going to it unless you have a problem.
You don't know who installed there.
We're not going to install this incorrectly, but
Well, you could, it's possible.
it's possible.
I've seen it.
But you don't be an idiot to install it.
I've had somebody test them with this little machine thing with lights and whatnot, and people have switched over before.
I might want to say don't try this at home. Just
Like,
Maybe you should.
if you plug something upside down, it still works though. If it has no ground, you plug
Right.
it upside down.
Right, but not with this. I mean, you can't have this be your neutral. Maybe you could have this be your neutral wire.
Because there's two wires up here, there's like one wire right here. Because like one's green for the grounding, the hot, and neutral. Right?
But if this is your hot wire, your device isn't going to work.
Oh, it's not.
Alright, so you can stick a paper clip there, or you can stick it here. And
No,
this is the short side.
Oh.
But sometimes electricians can't get them switched, can't get these two switched, so that's not a good idea. Just don't do it at all. But you can tell your friends that they can do it.
Oh, yes. You and your friend get to messing up the design.
Is hooked up correctly,
They won't die.
everything upside down, does it still work properly? Since it's AC?
Yeah, so the only reason this is an aside, but the only reason that you have these polarized, that is that one is definitely hot and one is definitely neutral, is that sometimes on devices, like say a lamp, check that out. On a lamp, you have two wires that come in. Right, you have a wire that comes in up here, and then you have a wire that comes in up here. They try to design the lamp so that the hot wire is as short as possible. All right, so that there is as little possibility for you to have a short within the device as possible. So they try to make the hot wire really short.
Do you ever put together those lamps that I see in a lot of dorms? Like it's really hard because that one wire is super short and it feels like it's not long enough.
Okay.
Through the rest of it.
I'm not sure. Yeah, I assume that's probably why. But anyway, that's an aside. So that's why they're polarized, because people, when they design devices that don't have that third prong, that aren't grounded, they try to make the hot wire as short as possible. All right. So the third prong offers a direct path to the grounding rod. Outside of your home. And what this does, this is the primary purpose for it, is to protect you from faulty devices. May I go down? So say, for example, you have this appliance. It's a toaster or whatever. Oh no, let's say it's a computer. So this is a computer. It has a metal case. Some computers don't have metal cases anymore, but let's say it has a metal case. You have electricity that comes in the hot wire. So it comes in this way. Actually, I had it drawn the other way, so I'm going to draw it in this way. I have electricity that comes in this way. It flows through the device, and then it does whatever it's supposed to be in the device. Goes through resistors, capacitors, whatever, and then it comes back out and goes back out to your meter. Now, if you imagine that something happens, like you get a wire that breaks or melts or whatever, then you get this wire that is going to go and touch the metal case. And then when you have current that comes in, it goes here, and then it charges all of this case. And it's just waiting for somewhere to go. And then, of course, you come along and you touch the metal case, and the electricity goes through you.
Of course.
So this grounding, what it does is that if you've ever looked inside your computer, for example, you see a little green wire that comes out of the power supply. Where does that green wire connect? You ever seen this? Huh?
The green wire is the starting wire.
To the what? Right, to the frame or to the case. So if any electricity, if that case ever becomes charged, then it doesn't go through you. Instead, the electricity goes out that green wire and then goes directly to that grounding rod outside your home.
Because you were touching.
even though you're touching it, because a copper wire is a much easier path for electricity to flow, a much lower resistance, so that current will go through the copper wire instead of through you. So it won't go through you at all, because you're a big resistance. You're like 100,000 ohms or something, versus, you know, a milliohm for copper wire. Scott?
The green, specifically green wire, because from what I remember, from your actual power supply, if you open up your desktop computer, the green wire that comes from the power supply is actually the startup wire.
Okay, what?
I know there is a wire somewhere. They have to
Yeah.
connect directly to the case, but I don't think it's the green wire.
Okay. I've seen it as green before. I could be wrong about the
It
color.
may be older
What?
older computers.
Maybe so, yeah. All right.
Fuses.
Right, fuses. Okay. But anyway, there's a wire that connects to that grounding, that third prong. So this third prong provides an alternate path to ground, which protects you from faulty devices. And it connects directly to that grounding rod outside your home. All right, one more thing, and that's the GFI. Oh, let's try this, actually. So on the next test, you'll see some simple questions about household circuits, how they're laid out, and how these various safety features work. Nothing terribly complicated. If you have a calculation, it'll be a simple one like we did in the last one.
So that's what gets really annoying for the lab fumes. The fumelets of the GFCI.
All right, I'm going to stop at 45. All right, A is right. It's not stability for the plug, though it does seem to make the plug more stable, like in the outlet, but that's not why it is. It's an alternate ground. All right, the last thing is the GFCI. GFCI looks like this. It stands for Ground Fault Circuit Interrupt. All right. Where do you find these GFCI outlets? Where? In the bathroom. Where else do you find them?
Maybe kitchen.
Okay, yeah, in your kitchen. In the lab, maybe, yeah. Where else?
All the fumelets.
By sinks. Right. You also find them outside. Like if you have outside outlets, they're most often GFCI. So these are all areas that are prone to be wet. Right. So GFCI is often in areas that are prone to be wet, such as bathrooms, kitchens, outside, etc.
Apparently I have too old for that since.
Right. You can often on hair dryers, actually newer hair dryers, they have the GFCI built into the plug. That way, if you're using them on a non-protected circuit, like a non-GFCI circuit, then it'll have it built in there. The GFCI is a very sensitive ammeter. Ammeter measures what? Current. It measures current. And if IN ever exceeds I out, the GFCI will turn off in a millisecond or less. So a very short amount of time. So it measures the incoming current and the outgoing current, and it asks, is this bigger than I out? So if you imagine that you have this device, hair dryer or whatever, you have current coming in, and then you have current coming out. What does it mean for I in to be bigger than I out? That means that you're losing current somewhere in the device. So normally, that would mean that you have current coming in, and then some of it goes through you, and then the rest of it goes back out here. If I in is ever bigger than I out, that's very, very bad, right? Because that means that you're losing current somewhere, and probably through a person, somebody that's touching something. And so it always checks that. Is I in bigger than I out? And if that's ever the case, it turns off. You have these buttons. I'll show you this in just a second. These buttons are used to test the ammeter. That ammeter can fail. I don't know if y'all burn up any ammeters in the lab, but they're fairly sensitive and they can be damaged. And so you're supposed to check these like once every month. And if you test it, it'll go off if it's okay, and then you reset it and it comes right back on again. Let's try these last two questions. I want to show you this thing and then we'll be done. All right, so what does GFCI do? We're looking at this top question here. I remember GFCI is very similar to circuit breaker, but they do different things and they operate in different ways. All right, I'll stop at 25. All right, A is good. That's right. Oh, did you not have time? I gave you 5 seconds. 5 second warning.
I was clicking at the same moment that you hit it.
I'm sorry. I thought we had everybody. 16. I think that's how many. 2, 6, 10. Yeah, we have 16 people. You must have
Well,
gotten
I
in.
guess I hit it twice.
Okay. So GFCI is that. B, I don't know what that is. Clear path to ground. That's that third prong on our plug. And then this last one is the circuit breaker. And let's try this last one. Which of these statements is true? All right, you have 1 second. All right, stop. No.
That's all right. Oh man, it's playing this song.
All right, I'll stop at 50 seconds, so just 6 more seconds, 5 more seconds. All right, let's see, A and B. Okay, this is true. Number 1 is true. They all operate at the same, does that say current? That is not true. They don't operate at the same current. They operate instead at the same voltage, right? As you add more devices to the household circuit, potential across each device decreases. That's not true. That's why they're laid out in parallel, so that's not true. And the circuit breaker turns off if IN is greater than I out. That's not true either, right? If this said GFCI, that would be true, but that's not what it says. Or if it said that the circuit breaker turns off if the current exceeds a certain amount. So just 1, A is the right answer. There is a question, by the way, on the test similar to this. It'll be different factoids, but they're like this, just sort of these basic ideas. What are they and what do they do? All right, let's look at this thing. This is kind of cool, actually. This is like a model of your wall.
This factoid is the word for today.
Yeah, if you want to use that today, that would be great.
I get one the way to use any of the words. Without some.
Y'all can come up if you want and see. This is kind of cool, actually. You might need to come up and see. So this is like a model of your circuit in your home. I'll set it right up. Oh, that's not good. I'm going to plug it in. So this would be like plugging it into the transformer. And in fact, if you look at this, you'll see that there are 3 wires. They've left some of it open. There are 3 wires. That's going to be the hot wire, the neutral wire, and the ground wire. Notice the ground wire. Which one is it, you think? You'll see it? Copper. It's the copper wire. It's bare. It has no insulation on it. Because normally there's nothing in it, unless there's some problem in your house. And the black is hot and the white is neutral. So if we plug this in, this is like plugging it into the transformer. All right, so we have a parallel circuit that runs through this. So if you imagine, each of these wires is like a loop, right? And so this is a dimmer switch. I can turn on the light. See, the light comes on, and you can make it brighter and dimmer. Watch this. This is kind of cool. If I turn on the heater, it shouldn't change what the light bulb does, right? But remember we talked about how the wires actually, they have a certain amount of resistance. And so it's as if I actually have this extra resistor that's over here in series with the parallel branch. And when I turn it on, it's actually going to draw a certain amount of current and change the potential to the light bulb. So watch this. If I turn this on, see how the brightness of the bulb changes as I turn on the heater? This heater draws a lot of current, and because the wires have a certain amount of resistance, it causes a drop in potential across the actual wires. That's kind of cool. So if you ever have a bathroom heater and you turn it on, you'll notice it affects things a little bit. Also, this is the GFCI right here. You can test and reset it. Now the heater's on right now. The thing about GFCI is if you have a GFI here, it's going to protect every other circuit or every other outlet that comes after it. So if I test this, it turns off the heater, and then there's my bulb. It's not on the same circuit as the GFI. And if I turn it back on, the heater comes back on. All right. So this is just sort of how your house is laid out. Again, here we have the light, which is on a separate circuit from the outlets. Have any questions?
Would you be willing to do your paper clip trick on
No. All right. All right, guys. You all have a good day. On Friday, we'll have a review for the exam, and then so if y'all spend as much time as we need going over that stuff, but I encourage us to continue on with chapter 5 as well. Hopefully,
Didn't really answer.
what's the right way? It doesn't matter.
Yeah, the answer.
Right. So see, these are the same way. They can go either way. This is actually a transformer. It's sort of like the transformer that you have outside the home. And it takes high voltage electricity and it converts it to low voltage. And that's a converter. So, yeah, AC/DC power is not sure. It'll convert it to a lower voltage of 5 volts.
What's scary if there was a technically right way,
No,
a wrong
it
way.
doesn't matter on this.
Oh, yeah, I was gonna tell you sometimes, like in our bathroom, the light goes turn over.
It goes what?
It goes like,
Yeah.
sometimes it goes bright, just a second, it goes back.
That's probably because there's something else that's coming on or off there. Is that
I don't know, I wouldn't know specifically, but that has something to do with how, in the way that it's laid
Yeah,
out.
watch for it, yeah. So like if you have a bathroom heater,
I mean, it's not, well, in the bathroom here, it's not in the bathroom, it's on, anything else in it. Just sometimes it just, for no apparent reason, like, when you turn it on at first, it goes really bright, but then it dims down really fast. Like when you turn it on.
it shouldn't do that really.
Yeah, that's what I thought too.
Yeah.
Maybe I need to get someone to
Yeah.
do that.
Makes sense.
Have a great day.
Bye. Hey, phenomenal. Andrew, I hope you get your grades up today. I'm very sorry this took so long. I know you are anxious. They look good. They look good, the grades.
We need to go?
Do you know that there's the, what you call it, different
Have the stuff to do. Let me ask her.
temperatures
if I
for
can miss it.